In this video, I'm going to talk about analysis of variance starting with the one-way ANOVA, followed in the next video by commentary on factorial ANOVA. And this part refreshes our memory on material that I covered in class. The key thing here is that we're computing these three different types of sum of squares: the total sum of squares, the between group sum of squares, and the within group sum of squares. Each one of these has its own formula. And when we compute the total sum of squares, what we're doing is we're taking every score, symbolized here by the letter X, and subtracting the grand mean from each of those scores for the entire experiment, no matter how many groups you have. The grand mean is the mean of everybody in the experiment. So if we had 4 groups with 3 people in each group, that would be a total of 12 participants. And the total sum of squares would be every one of those 12 scores minus the grand mean, which is the mean of all 12 of those people. And then you square each of those scores individually. After you've squared all those deviation scores, you add them up. And then you have the total sum of the square deviations, or total sum of squares. For the between groups, what we do is we observe the different brackets and parentheses which indicate a different order of operations. The first thing to do is to take the information inside the parentheses. And this tells us the symbol here is x bar sub j, or we can say mean sub j. And this merely refers to the fact that you're taking the mean of an individual group. So rather than an individual score, which is what we have here for the total sum of squares, for the between group sum of squares, what we're dealing with is the mean of a particular group. And that group is symbolized by the subscript j. If you had 4 groups, you would have mean sub 1, mean sub 2, mean sub 3, and mean sub 4. That's all that it means. So we don't actually do any computation with that. We just calculate the mean of each individual group by itself. Take the grand mean, subtract it from each group mean one at a time, square that deviation score, and then multiply it by the number of people in the jth group. If you had 3 people in group 1, but if you had 4 people in group 2, then the n here will change when you transition from group 1 to group 2. And this formula, in this way, this formula can accommodate having different number of people in different groups. In other words, it works even if you have different sample sizes for the different groups. There is a shortcut if all of your groups are the same size. I prefer this formula. Simply because it can be used in any situation, whether you have equal sample sizes or not. And then the third one here, the sum of squares within, is a measure of how much variability you have inside each group independent of all the other groups. And you see that we have a double subscript. X sub ij refers to the ith individual in the jth group. If you have 4 people in group 1, and you wanted to designate the second person in that group, that one score that is the second person in group 1, this designation would be x sub 2 for the second person, and then 1 for the first group. But we don't normally do this. We don't normally designate individual scores this way. Really what this is telling us to do is to treat every group independently of each other and take the scores inside group 1, subtract the mean of group 1 from each of those scores, square them and add them up. And then we'll do the same thing for group 2, group 3, group 4, however many groups we have. But we can skip this part. We don't really have to do this because what we know is that if you have any 2 of these, you can easily find the third one. The total sum of squares is divided into the between groups and the within groups. In other words, the total amount of variability gets chopped up part of it goes into the within sum of squares, part of it goes into the between. So if you calculate this one, I'm trying to highlight it here. If you calculate this one, and then if you calculate this one, there's no reason to go through this entire computation. You can just take the within, or rather take the total, subtract the between, and you'll have the within. And in our table here, the parts that we need to fill in are shaded. The three sum of squares go here. If you have any two of these, you can easily figure out the third. And it's the same process for the degrees of freedom, where the degrees of freedom here would be k minus 1. This one is n minus k, and this is n minus 1. And the document that I provided walks us through that. So here's a blank version of the table. What I'm going to show you is the calculation of these numbers with an example. And then I'm going to open up an SPSS file and show you how to enter the data. So here's the designation for the different types of degrees of freedom, the between groups, the within, and the total degrees of freedom. And here's this fake data set. So we've got the psychotherapy and drug treatments combined, that's PD. And by the way, if you were writing up a study based on something like this, you don't say both. You don't say PD. You say the participants who received both treatments, or the participants who received both psychotherapy and drugs. When you write up experiments, you need to maintain the ordinary narrative structure of the English language. You don't use acronyms unless you've already explained what the acronym is. And we don't use abbreviations unless it's a commonly used abbreviation. Okay, so we've got the group that uses both of these treatments, the group that only gets psychotherapy, the group that only gets drugs, and then the control group. And as I mentioned in class, this data set comes from the textbook by Rosenthal and Rosnow, Essentials of Behavioral Research. There are a lot of great examples in that book. You can find the full PDF for that book online because the authors have made it available freely. So first, we'll walk through the sum of squares total, the calculation of SS total, and you see that's what I've done here. I first calculate the grand mean, which is 4.5, and you would get this number if you added up all of this. I see you've got a typo here. Let me fix that. You would get the grand mean if you added up every individual score, all of these scores here, and divided by 12. But you can also take the group means, in this case 8 plus 4 plus 4 plus 2, and then if you divide that by 4, you'll have 4.5. The next thing is that we take the grand mean, subtract it from each score. So 9 minus 4.5 leaves us with 4.5. 8 minus 4.5 leaves us with 3.5, and so on. You then square those numbers, because some of these numbers are going to be negatives, and we don't want negatives. We square these numbers to get the sum of squares. And the total amount of sum of squares, which represents the total amount of variability, is what you get when you add this one, plus this one, plus this one, and this one. And you can see the calculation down here. The summing of these different parts of the sum of squares adds up to 77. We're going to put that right here in our table. The next part, we can compute the sum of squares between, and this one is, I found over the years, a little bit more tricky for students just because the formula itself looks a little bit odd. And the key thing here is that if you have 4 groups, you're going to have 4 sets of brackets. You have to do this for each group. We take the mean of the first group, which is 8. How do I know that? I go back here, and I can see the mean of the first group. So the mean of the first group minus 4.5, which is the grand mean, square that number, and multiply by 3. When you do that series of computations, you get 36.75. But you don't stop there. You have to keep going. So then we take the mean of the second group. We see that right here. The mean of the second group is 4. And we plug that in here, subtract 4.5, which is the grand mean, square that number, and then multiply it by 3. And when you do that set of computations, the part that I'm highlighting right here, when you do that, it comes out to be 0.75. And then for the third bracket, the third pair of brackets, that computes to 0.75 as well. And the fourth set of brackets computes to 18.75. You then add those up, and that is the between group sum of squares. And that is essentially your signal in terms of a signal to noise ratio. This is the amount of treatment effect that there is. This is the amount of the variability that can be thought of as differences between groups. We're going to put that here for the between group sum of squares. And because of the additive nature of these three, I take 57, subtract it from 77, and that answer goes here. You can see that I've also put in my degrees of freedom. K minus 1, we had 4 groups. So K minus 1, K is the number of groups, 4 minus 1 is 3. The within groups is N minus K, and so that's 12 is the total N for this experiment, this hypothetical experiment. 12 minus 4 is 8, and then 12 minus 1, which is N minus 1, 12 minus 1 is 11. And you can see that these also have the additive property. 3 plus 8 equals 11. And so now we can solve it because 57 divided by 3 will yield the mean of that sum of squares. So literally what we're talking about here with the mean square is the sum of squares that we're looking at here, the sum of squares for the between groups, divided by 3, in other words, averaged across its 3 degrees of freedom, yields an answer of 9. And then the same thing here, 20 divided by 8 gives us 2.5. We don't do the computation down here. There's no reason to. It doesn't mean anything. This part here is the key to the ANOVA, and that is the signal to noise ratio, where the numerator is the amount of treatment effect and the denominator is the amount that is not treatment effect, in other words, noise, the random variation that everybody has. It's because some people feel better or worse on that particular day. 19 divided by 2.5 gives us the final answer. Word is not cooperating with me here. Here we go. 19 divided by 2.5 leaves us with the answer, 7.6. And then if I were writing this up, I would write it up as F parentheses 3 comma 8 close parentheses equals 7.60. So that's that. Let me transition now to SPSS. I've got it booted up. And what we want to do here in order to make sure that we have the right answer, we want to enter the data and see that we got the correct answer. So I'm going to create my variables in variable view. I have 2 variables, the independent variable and the dependent variable. We'll call the independent variable group, and the dependent variable is score. That's how I usually like to set it up. I toggle down here back to variable view, and now I need to tell SPSS who's in what group. I've got 3 people in the first group, 3 people in each of the 4 groups. So these represent the 3 people in group 1, the 3 people in group 2, the 3 people in group 3, and the 3 people in group 4. Now I can enter my data. I've got a printout telling me what the data are. So that piece of paper you hear moving around, it's my data sheet. 987, 642, 543, and 420. So now you see that the data has been set up in order for me to analyze it as a one-way analysis of variance. I go now to analyze, compare means, and you see the different options here. I can do a one sample t-test, independent samples t-test. And by the way, if you wanted to do that, you can designate which groups you wanted to run here. I'll show you that in a second. But let's do it the right way first. Let's do a one-way ANOVA. So I enter my independent variable down here under factor, and I enter my dependent variable up here where it says dependent list. Now I have a number of options here. Let's check them out. Primarily the ones that we're interested in are the descriptive statistics. That will give us the mean and standard deviations for each group. Homogeneity, a variance test which tests one of the important assumptions about the F test. Remember that these are two different tests altogether. I'm going to ask for the Brown-Forsyth just because if the homogeneity of variance assumption is violated, the Brown-Forsyth is the one that we want to use. And we don't need those other things. So let's just stick with that. And then I click post hoc, and you see the different options: the LSD test, the Bonferroni, Sidak-Chaffee. Bonferroni is the most common, although as I argue in one of my handouts and in class, I argue that the Bonferroni is a terrible test to use, but we'll go ahead and use it anyway because that's what people want to see. That's what most researchers use. So we'll go with that and click OK. And so now I've got to reshape this. I have it set up for a narrow window on my screen for the recording. Here's the output. You can see the mean and standard deviations of our four groups: group 1, group 2, group 3, group 4. Maybe I should have put variable labels in there. I'll show you how to do that too. Let me run it again, but let's just take a look at this. If you were reporting this, normally you do not give the total. The total is the grand mean. So we can check to see what the grand mean is, but normally we don't report that. We see that the Levine statistic, that's the homogeneity of variance test, is not significant. That's a good thing. We don't want it to be significant. That tells us that we have not violated the assumption of homogeneity. If we had violated that assumption, we would have to use the Brown-Forsyth adjusted statistic, which you can see is the same as our regular one here. And the reason why that's the same is because the variances are almost equal. Here's your Anova summary table, and you can see that we got the same numbers here as we computed using the formulas. The additional thing that we see is the exact p-value, p equals 0.01. And then we have the pairwise comparisons. This part is really a lot easier to use if I have the variable labels. So let me go back in, and I'll show you how to do that. Go to variable view, and under group 1 was both. Now remember, you do not describe this, if you're writing it up, you do not describe it as both. You describe it as the participants who received both of the treatments. But I don't want to write all that in here, so I'm just going to call it both as an abbreviation. Group 2 is psychotherapy alone. I'll call that group psycho. And group 3 is drugs. The psychos are on drugs. And group 4 is the control group. So I type that in, click OK. And now when you want to go back and revise that, if you do, you can click on that little button on the side and you get the pop-up. But that's exactly how I want it set up. You see that nothing changes here, although if you go to View, Value Labels, it will toggle the labels on and off. So that way we can check easily who's in what group. And I usually like to use the numbers. So I'll go back and analyze it again. I don't have to do anything else. It's already set up the way that it should be. So I'll just hit OK. And now the only difference that you see is over here. We have, instead of the numbers for the groups, we have the names. And that can be a very useful thing. And then down here, it's easier to read the post hoc tests when you have the labels in here instead of just numbers. So of those who got both psychotherapy and drugs compared to the psychotherapy alone, we have a non-significant result. It's 0.088. And then of those who got both psychotherapy and drugs compared to the drug group, it's also non-significant, but compared to the control group, it is. And so you can see that you have a variety of different results here. Be aware that these results repeat themselves. So if you see, like here, both versus control, if you go down to control and both, you see that you get the same thing. So this p-value is identical to this p-value because it's exactly the same comparison. I don't know why they have it set up like that, but they do. It's irrelevant. You do not want to report all that information. Only report the tests once. So that's the walkthrough on running an analysis of variance, a one-way analysis of variance based on raw data. Let me show you also, while I'm at this, the way to do an independent samples t-test if we were interested only in two groups. So we know that based on the numbers that we're looking at here, we know that the both group, the group that got both psychotherapy and drugs, has a mean of 8, and the control group has a mean of 2. So if that's the biggest difference between groups, maybe we should just look at those two in a t-test. And if we wanted to do that, we could do that. We don't have to do anything special in terms of rearranging the data. If you go to compare means, independent samples t-test, we can run this comparison where we put group down here, and you see that it's got the question marks, and it asks us to define the groups. It can only compare two groups at a time, so we have to tell it which two we want. We want group 1, which is the both group, versus group 4, which is the control group. And this will run a single independent samples t-test of group 1 against group 4. And then we can put our t-test, our dependent variable rather, over here. Check options to see if there's anything in with t-test that there really isn't. Everything is already built in. And we run our t-test and we get actually the exact same p-value that we got with our Bonferroni test. So that's interesting, but not particularly relevant. It's not always going to be that way. But you will see that the means here are the same as in the descriptive statistics up here. The mean of 8 and 2. 8 and 2. And so that's how you can do an individualized t-test within a larger data set if you're interested in doing that. And that is the walkthrough for one-way ANOVA. Join me next time for factorial ANOVA.